I think it's time that we start this afternoon session, which is entitled Discussion Project Contest. And I am Massimo Altarelli. I was for 11 years the project leader of the construction of the European XFEL. And after my retirement, I took a research job at the Max Planck Institute for Structure and Dynamics of Matter in Hamburg. So in this session, we are going to have sort of, all the beautiful science dreams that we heard about start to meet the boundary condition for the actual realization of the project and the construction of the facility and of the instruments. And then we will have two talks bringing us up to speed on the future plans of existing facilities, namely the European XFEL and the LCLS. Okay, so having said that, the first talk is about the UK XFEL conceptual design process by Jim Clarke and David Dunning. I don't know how they organize themselves for this joint performance. Okay, go ahead.
Good afternoon, everybody. So I'm Jim Clarke, I'm the director of Aztec, and Dave is also in Aztec. We're both from Daresbury Laboratory, and we're going to be talking to you about the actual conceptual design project that we're just starting. So I'm going to give you sort of the context and the background to the project, what our plans might be, and then Dave's going to go into a little bit more detail about the challenges we are going to tackle. So we're officially doing the Conceptual Design and Options Analysis Project, it's sometimes called CDOA. And as was mentioned first thing this morning, this is funded by something called the UKRI Infrastructure Fund. So UKRI is the UK Research and Innovation, the umbrella body that sits above STFC. So it has this new infrastructure process, which is, as was explained again this morning, it's a much clearer, transparent, step-by-step process for new infrastructures across whatever part of the spectrum UKRI covers. And the good thing about this process, again, as I mentioned before, is it doesn't just fund massive projects, it also funds the scoping studies to start these projects off. So CDOA is just benefiting from one of these funds. So it's officially called a preliminary activity, and it's got a budget of £3.2 million over 3 years. And we officially started on the 1st of October, so we've been running for a few months so far. So we've got, over this 3-year period, we've got some aims to achieve. Obviously, we're going to explore how best to achieve the next generation XFEL capabilities identified in the science case and articulated earlier, and also as the science case evolves over the next couple of years. And then we're going to develop a number of options, including a conceptual design for a unique new facility based in the UK, but also looking at potential investment into existing X-ray FELs, aligned with their future plans, of course, to enable access to these acquired capabilities for a different route. And then finally, we have a deliverable, which is obviously the conceptual design report, which compares all these options in terms of the research capability and the capacity that they would offer, cost, benefit, risks, and sustainability. So in terms of what might come afterwards, so we're expecting the CDOA phase, assuming we get through these stop-go decision points that Mark Thompson articulated. The next phase will be a technical design phase. So this is quite conceptual. Then we go into much more detail with our chosen option. That's likely to include prototyping and other risk mitigation activities. And then that would be followed by a construction phase. Obviously, these phases are not yet approved or funded by UKRI, but we are starting as part of this phase to scope out what the next phase would be. And that's an important part of our work. And I know the question will be, how much is this XFEL going to cost? And of course, it depends exactly which option is recommended in the end, which one is adopted by UKRI. And the same for timescales as well. Obviously, building a brand new facility in the UK is likely to take longer than investing into an existing facility. So I'm not going to give any comment on location, on cost. I also get asked about location. I've already been asked several times today, where's it going to be built if it is in the UK? And we're not taking any account of location at all in this phase. So we're just assuming a blank piece of paper, a greenfield site. We're not assuming it's aligned with any particular location in the UK, if it's the UK option. Obviously, we have no idea about cost yet, but for reference, we can look at the costs of facilities that have been built. So, for instance, Swiss FEL was 275 million Swiss francs in 2013 money. European XFEL 1.2 billion euros in 2005 money. And the scale physically, Swiss FEL about 750 meters, European XFEL just over 3 kilometers. So it gives you an idea of the size and shape and scale we're talking about. In terms of who's delivering the CDOA project, so at the top we've got John, and then me. I'm the technical lead, and Paul is our project manager. We're broken down into 3 distinct areas under what's called the champions. So we've got someone who's looking after the international side, that's Ed Snedden. That means the XFELs outside of Europe. Then we've got Deepa Angle-Kalinin looking after the European XFEL interactions, and then Dave Dunning, who's speaking next, looking after the UK-based facility. Then we've got a design team underneath that. The science team has already been talked about earlier by John, and he also mentioned that we've expanded quite considerably last year. In terms of how we're going to work with the international partners, so we've actually already had quite a few Zoom meetings with the existing X-ray FELs. We've been explaining what our project is about and what we're looking for, and also trying to get a deeper understanding of what their existing plans are, or their sort of aspirations for the long-term future. I'm going to hear about that a bit later in this session for 2 of the facilities. We've been really well received by these facilities, which we're very, very, very grateful for, and it's been tremendously supportive. So thanks very much to the facilities for that. We've already had a face-to-face meeting. We sent out quite a large group to European XFEL, and some photos at the bottom there, just before Christmas, as you can see. And there'll be a visit to LCLS2 shortly, and then another one to Swiss FEL. Actually, Swiss FEL is going to come first. Swiss FEL is in March, and then LCLS2 later. So we're planning to develop the investment options with these FELs, obviously match closely with their own aspirations. We're not going to just go in and try and do something that's against their strategy. That wouldn't make any sense. So we're trying to do this very collaboratively with these facilities. But it's also got to obviously match to our science case. And then the last thing I'm going to mention before I pass over to Dave is about sustainability. So this is actually something which is quite new this time compared to some of the previous projects, where sustainability now is clearly a massive issue internationally. UKRI wants to achieve net zero by 2040. Building a brand new facility that's going to use lots of electrical power, etc., has to fit in with that. So we're looking at all the options we can to build sustainability into this facility. The UK accelerator community, actually, interestingly, is really active in this area. And this was way before XFEL got off the ground. So, for example, we're very strong on using permanent magnets instead of electromagnets. We've got some very active research going on different types of superconducting RF, which can run at 4 Kelvin instead of 2 Kelvin. And that makes a huge difference to the power demand for the types of linear accelerator that is there needed for the megahertz rep rates. And we're also working on more efficient RF power sources and faster RF cavity tuners, both of which save electrical power. And on the broader issue of carbon footprint, we've also got activities in the UK looking at where the carbon goes in a life cycle of an accelerator-based project. So this work will continue. It's going on in parallel, but it will feed directly into this project as well. So now I'm going to hand over to Dave, who's going to tell us a bit more about the details.
Okay, thank you very much, Jim. Okay, so I have the fun job of explaining the challenges for a facility like this, which I see as coming in 3 main areas. So the first part is understanding the specification, all of the things that we talked about this morning. It's interesting because it's not just one single specification, but it's several interlinked sets, lots of ideas of what the next generation machine looks like. And it's not fixed. This is going to continue to develop over the course of this phase of the project, and also through the lifespan of a facility like this. Another challenge is developing specific technical solutions, and I've got a list of examples of these in the following slides. And it's also about developing compelling facility proposals. We've already heard about how we have to consider a UK-based options as well as international investment options, but it's also the compatibility of the technical features, the overall scope of the project, the international context. Sustainability, Jim's just mentioned, and as well socio-economic factors. This shows a very rough timeline for the project. So the focus so far, as well as setting up the project and organising events like this, has been on understanding the science requirements with this survey, meetings with the science team, setting out a first pass of the specification. And we're now into what we call the gap analysis exercise, which is basically analysing the specification against what exists at existing facilities, against existing technologies and where they will go in future, and between the technologies. For example, if we do X, then we cannot do Y, or we need A in order to do B. And the idea is that we'll focus this process over the course of the coming months so that we'll be able to design. Just what? No. I can use that. So that we can focus this down and design concepts for these facility options by the end of the first year, so that we can go into the core work in the next 2 years following this, just to bridge that gap between what's available now and where we need to go in future, all the while iterating with the science, with these series of science workshops. So one of the first major activities of this phase, as I've said, was a detailed survey to ensure that we've captured the requirements from the science case, any updates since then. Thank you very much to all the people who contributed to that, lots of speakers this morning, lots of people in this room. And it is still open for input, so contact the team to contribute. And just to give an idea of how this worked. So in part, it was a tick box exercise. So this is an example of one individual response, at least to the tick box part of the questionnaire. So you can respond thinking on quite a granular level, so a kind of experiment by experiment level, and looking far ahead in the future. What kind of photon energy range do you want? What repetition rate, energy per pulse, and so on. And this, it will even allows you to input multiple FEL pulses. This one shows 2 FEL pulses with broadly similar properties. And what we did then was we clustered the responses to show different sets of specifications. So this, to some extent, comes back to Massimo's question earlier, how it's grouped. The colours here are the different sections from the science case. So you can see that they broadly did group. I mean, there's a few other clusters here not shown, but in these cases, they clustered by the sections of the science case, but there are all obviously some outliers of different colours that don't fit in there. Obviously, we can't do everything with a tick box exercise, text box entry. There's lots of meetings with the science team. There's events like this to keep discussing this, and there's the upcoming workshops as well. I'm now going to run through the key next generation capabilities from the science case and some of our thoughts on the technical solutions. So the first one, as John has said, to some extent this mirrors John's talk, but with more focus on the technical solutions, is a transform limited operation across the entire X-ray range with pulse durations ranging from 100 attoseconds to 100 femtoseconds. So first off, to say it's very challenging to do this, but also exciting to generate laser-like X-rays across this wide range of photon energies and pulse durations. It requires a range of advanced FEL techniques. So I'll describe that on the next slide, but also see the emerging technology session this afternoon. They all have challenges regarding tunability, high repetition rate operation, and another major challenge above all this is to run many of these modes in parallel, which we think is a major opportunity to be a key distinguishing feature of a new facility. So this slide goes into a bit more detail on transform limited operation, which basically means the best pulse quality that you can get for a given photon energy and pulse length. We're looking to cover a very wide parameter space, so 3 orders of magnitude in both photon energy and pulse length or even more. To do that, you can't all do it with a single FEL technique. So for the 100 attosecond end of the range, we'd be looking to techniques like XLEAP, that's a leading candidate for this area. We would definitely do external seeding, which means using an external laser to control the properties of the FEL pulses. And we do this as far as possible to the highest photon energies we can and to as high rep rates as we can, utilizing advances in high repetition rate lasers and doing conversion, like harmonic conversion within the FEL to reach as high a photon energy as we possibly can. Where we can't do external seeding, we would look to techniques like high brightness SASE, which is a technique developed in the UK to deliver kind of few femtosecond pulses with very high peak power, like terawatt peak power, millijoule pulse energies, very narrow bandwidth, and crucially can be applied at any electron beam repetition rate. Self-seeding is already established in this space, but there are many ways to enhance it. And beyond that, to the longer pulses and narrow bandwidth, there's things like X-ray free electron laser oscillators. So the next key capability is even spaced high repetition rate pulses to match sensors and detectors. From the science case, we were talking about greater than 100 kilohertz in soft X-ray and greater than 1 kilohertz in hard X-ray. And just to say that the recent input indicates that if possible, 100 kilohertz in the hard X-ray would also be highly preferable. To do parallel operation of multiple experiments, all at 100 kilohertz, obviously means that we need an electron bunch repetition rate higher than that. So for example, 1 megahertz with multiplexing. And these parameters are critical. They really dictate the major facility choices as shown on the next slide. There are a lot of accelerator challenges listed there, but high repetition rate also brings benefits in terms of synchronization. There are also many facility-wide challenges, including data acquisition and management, sample delivery, detectors, and so on. But this has the potential to deliver a transformation in capability. So just to explain a bit more detail, the photon energy and rep rate requirements, we have this detailed input from the science case, which is the gray boxes, as well as from the survey, which is the colored points in terms of photon energy and repetition rates. And just to say that the maximum photon energy strongly influences the required electron beam energy. So put some kind of indicative numbers along the bottom, while the repetition rate largely dictates the type of accelerating technology. So I put some typical accelerator technologies on the right. And just as an indication, our preliminary focus for UK XFEL, we are thinking of something like an 8 GeV superconducting machine operating continuously evenly spaced pulses, bunches at 1 megahertz, separated out to 100 megahertz of experiment, which would put us in a really good position to cover a lot of the science requirements. But just for comparison, a machine like European XFEL has much higher electron beam energy than this. That means it has much greater potential to get to higher photon energies, but also operates in a different kind of repetition rate mode. Skipped a couple there. They also have their own challenges and opportunities. But to come on to the final one, the full array of synchronized sources, John or James perhaps would be much better to talk about the laser side of this, but essentially to say that we would want high repetition rate lasers pumping a wide range of wavelengths, centralized as far as possible with a suite of sources available on demand to users, and also a very high power, high energy laser, basically as large as the budget allows, using this kind of technology. And this is about coupling a key UK strength in lasers to key UK strength in accelerators, and two of those together, again, is a potential unique selling point for this machine. So, coming to the end, going to talk about the focus for the facility design. So how do we put this together? As I've said, we're still at the early stages of this process, but what we want to define so that we can to give some focus to the facility design team is we're going to focus on these two aspects. So transform them to generation across the photon parameter space. I think there's a clear scientific need and vision of this laser-like X-rays for users. It's a significant technical challenge. The output will be valuable to international user community and other FEL facilities. And also to focus on the operation of parallel beam lines, maximizing user throughput. So we're going down this very high repetition rate approach, maximize the use of every electron bunch and pound invested. We'll need fast data processing and multiple simultaneous user experiments. A wide range of synchronous sources will be required, high availability operation, and future upgrade paths driven by emerging scientific needs. But there are many things beyond the preliminary focus. As you've heard this morning, there are lots of ideas. There are several other technical capabilities we'd like to consider, not necessarily in detail to begin with, but they could impact the preliminary focus activities. So we need to be aware of these from the outset. These are things like very high pulse energy. We've had requests for 100 millijoules or even higher. Very high photon energies, 50 to 100 kVs. Other synchronous sources like gammas and terahertz. as several other exciting ideas that were mentioned this morning and also in the science case. And for each of these, we need to think about, are these an additional feature of a UK-based facility? Can we integrate these things? Would they be best delivered at another facility? There's a lot to think about how these things fit together. And finally, opportunities to engage. As you've heard, there's going to be science workshops every 3 months around the UK. We'll also be doing facility design events. We've got a meeting with some of the speakers tomorrow. We'll have more of these meetings as we go on. To join the team, I think Paul Aiden, our project manager, is the best central contact for this, but also you can come direct, as Paul's over there, or direct to relevant team members. And we've also got a new website, xfel.ac.uk, which has not got much on it at the moment. We'll get more as time goes by. It's got a very tiny button at the bottom that says mailing list. So please click on that and sign up to hear more about this project. And I've also shown a very tentative, probably already way out of date, timeline for the future, plans for this, workshops for this project. So I hope to see many of you at these events in future. So thank you very much.